Welcome to the second training module for GPI, the Graphical Programming Interface. I'm Nick Zwart, and today I'll be showing you how to generate a k-space filter. In this exercise, we'll be looking at a k-space filter network, which will demonstrate the function and interface for a few basic GPI nodes. This network builds upon the cross-section network that we looked at in the first module for visualizing our filter, and introduces the combine node for side-by-side comparisons, the FFT node interface for multidimensional FFTs, the math node for simple array operations, and the shapes node for generating window functions. Load the network by navigating to the Help menu, clicking Documentation, opening the Examples folder, and dragging the k-space filter network onto the canvas. It should look something like this. The key concept for this exercise is to familiarize yourself with the shapes node as a function generator and the FFT node's interface, both of which will be learned through practice in the hands-on portion of this exercise. But before we start, I'll go over the use of the combine node and show you how to resize an image in the viewport widget of the display node. Starting with combine. This small example network shows two shapes nodes, each generating a 256 squared array. Both arrays are passed to combine, which is outputting an array of 512 by 256. The two arrays are being concatenated, and if we look at the image viewer, we see that one of the shapes nodes is generating a circularly symmetric sinc function, and the other is generating a rectangular function with a linear taper. Looking at the combine menu, the combine dimension widget is set to a value of 0, indicating that the two arrays were appended along the 0th dimension. When we change that to the first dimension, the appended side changes as shown by the image as well as the edge tip. To create a 3D concatenation, the image display node must first be disconnected since it cannot view 3D arrays. To test, we'll first connect the statistics node and then set the combine dimension widget to a value of 2. The edge now shows 3 dimensions. In this network, we have the shapes node generating a larger 2D array, one that is not completely visible within this window. So if panning or window sizing are not sufficient, we can double-click the viewport widget to get some extra options and zoom by changing the scale factor value. Now take some time to familiarize yourself with the shapes and FFT nodes by completing the following tasks. Start off by changing the filter from a high to a low-pass filter. Then upsample each image by a factor of 2 along each dimension using the FFT nodes. And finally, give the filter a transition band that stops at the outer edge of sampled k-space. You can now pause the screencast. Alright, time for the solution. Let's review the network. Multi-slice image data is being read in as a numeric array. The vector element is being converted to the complex data type, and an axial slice is taken from the data set, just as we covered in the previous module. We are also taking cross-sections of the filter to visualize the transition band. The filter is being applied in the frequency domain by first taking the FFT, then multiplying by the filter array, and then back with the inverse FFT. The original and filtered image arrays are concatenated so that they can be compared side by side in a viewer window. The 2D view of the filter shows that it is a high-pass filter. The low spatial frequencies are being zeroed as indicated by the black color, and the high spatial frequencies are being passed as indicated by the white color on the periphery. This is also indicated by the pass value and stop value widgets in the shapes menu. The low-pass filter is made by simply flipping these values. And now the resulting image is a lower resolution version of the original. To upsample the non-filtered image, we need an FFT pair for zero padding. We can copy and paste the ones used for filtering, transform the original image, and then pass it to the inverse transform. To zero pad before transforming, Open the second FFT node that's set to inverse. The menu shows that the FFT for each dimension is turned on. The dimension scale factor is set to 1, and therefore the dimension length is the original size. We want to double the size of each dimension, so we'll set the factor to 2. Now the filtered image is the original size, and the non-filtered image is 4 times larger. When they're both sent to combine, the output port turns yellow, indicating that nothing changed. This is because combine can't concatenate 2 arrays along a dimension with differing lengths. To fix this, the filtered image is padded by a factor of 2 in each dimension, and the images are scaled. We can fit both in the window by resizing the image. Before adding a linear transition band to the filter, we can look at the sampled K-space by borrowing the image viewer and connecting it to the transformed image. By capping the pixel values, the sampled K-space boundary becomes more apparent. In this case, it's circular because it was a spiral acquisition. This tells us that a circular, or in this case elliptical, window function will fit it best. It's shown to have a linear transition along the cross-section and a differing kx and ky transition band. By toggling the equal dimensions widget button, both are set to the same transition. Now the width just needs to be adjusted and the transition band stops at the radial extent of the sampled K-space. The filter can be viewed by clicking the 2D filter display, and we can also compare the 2 frequency domain images before and after the filter is applied. The final result can be seen by connecting the viewer back up to the combined image arrays. Well, we've looked at a few nodes and some potential ways of using them. This example provides a simple and yet commonly used algorithm in MR reconstruction. You can find more information by visiting gpilab.com.